Hello everyone. Can you hear me? Um okay, so let me change to full screen. Oops, hold on. Okay. So last stream I learned about the semaphores. They're used for concurrency stuff. This stream I'm going to be learning about I'm just going to be reading the next chapter. It says concurrency bugs, so let's see what it's about. Seems to be 16 pages. What about this one? 12. Um So currently, I'm planning just to read this in this stream, but if I am in the mood, I might read the next one as well. So, common concurrency problems. Researchers have spent a great deal of time and effort looking into concurrency bugs over many years. Much of the early work focused on deadlock, a topic which we have touched on in the past chapters but will dive into deeply. More recent work focuses on studying other types of common concurrency bugs. In this chapter, we'll take a brief look at some examples of concurrency problems found in real code bases to better understand what problems to look out for, and thus our central issue for this chapter. Concurrency bugs tend to come in a variety of common patterns. Knowing which ones to look out for is the first step to writing more robust, correct concurrent code. What type of bugs exist? The first and most obvious question is this: what type of concurrency bugs manifest in complex concurrent programs? The question is difficult to answer in general, but fortunately, some others have done the work for us. Specifically, we rely upon the study by Liu et al., which analyzes a number of popular concurrent applications in great detail to understand what type of bugs arise in practice. The study focuses on and four major and important open source applications: MySQL, Apache, Mozilla, and OpenOffice. When I bought this laptop, which I'm currently using, I got OpenOffice already installed, and then I uninstalled it and bought MS Office. Anyways, in this study, the authors examine concurrency bugs that have been found and fixed in each of these code bases, turning the developer's work into a quantitative bug analysis. Understanding these results can help you understand what type of problems actually occur in mature code bases. Figure 32.1 shows a summary of bugs Lowe and colleagues studied. From the figure, you can see that there were 105 total bugs, most of which were not deadlocks. The remaining 31 were deadlock bugs. Further, you can see the number of bugs studied from each application. While OpenOffice has only 8 total concurrency bugs, Mozilla had nearly 60. We now delve into different classes of bugs a bit more deeply. For the first class of non-deadlock bugs, we use examples from the study to dive our discussion. For the second class of deadlock bugs, we discuss the long line of work that has been done in either preventing, avoiding, or handling deadlocks. So, MySQL database server, 14 non-deadlock and 9 deadlock. Mozilla has 41 non-deadlock and 16 deadlock. I mean, browsers are like would be very complicated because they're like compilers for JavaScript and HTML, right? Okay, let's see. Non-deadlock bugs make up majority of the concurrency bugs according to Lou's study. But what types of bugs are these? How do they arise? How can we fix them? We now discuss the two major types of non-deadlock bugs found by Liu et al. Atomicity violation bugs and order violation bugs. The first type of problem encountered is referred to as an atomicity violation. Here is a simple example found in MySQL. Before reading the explanation, try figuring out what the bug is. So we have thread 1, if thread proc info, f puts thread proc info, thread 2 thread proc info. Now, like it might reach this code, check that proc info exists, and then it evaluates as true. But then right before running this, a context switch would happen, and then the CPU will assign null to proc info, and then it will go context switch back to thread 1, and then when it continues from f puts, the null value goes in here. In the example, two different threads access the field proc info in the structure thread. The first thread checks if the value is non-null and then prints its value. The second thread sets it to null. Clearly, if the first thread performs the check but then is interrupted before the call to f puts, the second thread could run in between and thus setting the pointer to null. When the first thread resumes, it will crash as a null pointer will be dereferenced by f puts. The more fundamental definition of an atomicity violation, according to Liu et al., is this: the desired seriability among multiple memory accesses is violated. A code region is intended to be atomic, but the atomicity is not enforced during execution. In an example, the code has an atomicity assumption about the check for non-null of proc info and the usage of proc info in the f puts call. When the assumption is incorrect, the code will not work as desired. Finding a fix for this type of problem is often straightforward. Can you think of how to fix the code above? Yeah, I mean, I looked at the answer, but using a lock variable, using a lock can solve it. In this solution, figure 32.3, we simply add locks around the shared variable references, ensuring that when either thread accesses the proc info field, it has a lock held. Of course, any other code that accesses the structure should also acquire this lock before doing so. The red one, we use a lock with the identifier proc info lock. So this lock is being held by thread 1. This code will run. So even if the context switch happens in between, like right after the if statement, thread 2 will try to gain this lock, but thread 1 already holds this lock. So thread 2 has to wait for thread 1 to finish. So the context switch will happen back to thread 1. Thread 1 will complete and then unlock the lock. And then going back to thread 2 can now lock it, turn this into null, and then unlock. Another common type of non-deadlock bug found by Liu et al. Is known as an order violation. Here is a simple example. Once again, see if you can figure out why the code below has a bug in it. So we have void init mthread pr create thread let me see what's happening. So thread 1 init mthread, we create the thread, right? And then void mthread mstate thread state. We create the thread. We are using a main but the main function is using mthread. Another common type of non-deadlock bug found by Liu et al. Is known as an order violation. Here is a simple example. Once again, see if you can figure it out. As you probably figured out, the code in thread 2 seems to assume that the variable mthread has already been initialized and is not null. However, if thread 2 runs immediately once created, the value of mthread will not be set when it is accessed within main in thread 2 and will likely crash with the null pointer dereference. Note that we will assume the value of mthread is initially null. If not, even stranger things could happen as arbitrary memory locations are accessed through the dereference in thread 2. Formal definition of an order violation is the following. Desired order between two memory accesses is flipped. A should always be executed before B, but the order is not enforced during execution. The fix to this type of bug is generally to enforce ordering. As discussed previously, using condition variables is an easy and robust way to add this style of synchronization in modern code bases. In the example above, we could thus rewrite the code as seen in figure 32.5. So, if first thread 2 will lock, and then while empty init is 0. So let's say it starts with thread 2. While empty init is 0, we wait for this condition to become true. So empty init is initially 0. We have empty condition. Mthread main pthread mutex lock. Okay, so we lock it. We do init 1. So wait, if I remember correctly, it unlocks thread, right? So it unlocks this. So the other threads can like change the condition. So yeah, and then when the wait returns, it relocks it back. So anyways, we lock 1 and then signal to empty condition and then unlock. And then when the context switch happens back to thread 2, this is now fulfilled. So it received a signal from here. Now empty init is now 1. Empty init is now 1. And then it goes back here and unlocks the empty lock, which was locked by wait. In this fixed up code sequence, we have added a condition variable, empty condition of the corresponding lock, as well as a state variable, empty init. When the initialization code runs, it sets the state of empty init to 1 and signals that it has done so. If thread 2 has run before this point, we will be waiting for this signal and corresponding state change. If it runs later, it will check the state and see that the initialization has already occurred. Thus continue as is proper. Note that you could likely use a thread as the state variable itself, but do not do so for the sake of simplicity here. In ordering matters between threads, condition variables or semaphores can come to the rescue. Non-deadlock bugs. Summary. A large fraction of non-deadlock bugs studied by Liu et al. Are either atomicity or order violation. Thus, by carefully thinking about these types of bug problems, programmers can likely do a better job of avoiding them. Moreover, as automated code checking tools develop, they should likely focus on these two types of bugs as they constitute such a large fraction of non-deadlock bugs found in development. Unfortunately, not all bugs are as easily as fixed as the example we looked at above. Some require a deeper understanding of what the program is doing or a large amount of code or data structure reorganization to fix. So far, we learned about non-deadlock bugs, right? Now it's time for deadlock bugs. Beyond the concurrency bugs mentioned above, a classic problem that arises in many concurrent systems with complex locking protocols is known as deadlock. Deadlock occurs, for example, when a thread is holding a lock and is waiting for another one. Unfortunately, the thread that holds lock L2 is waiting for L1 to be released. Here's a code snippet that demonstrates such a potential deadlock. So thread 1, lock L1, lock L2, thread 2, lock, okay, receives this, but L2 is already locked. It's waiting for thread 1 to unlock L2. Thread 2 has lock 2 is waiting for L1 to be released. So wait. Thread 1 is holding a lock L1 and waiting for another one L2. Okay, wait, no, sorry. Thread 1 holds L1, thread 2 holds L2, but they can't go any forward from this. Okay. Note that if this code runs, deadlock does not necessarily occur. Rather, it may occur if, for example, thread 1 grabs lock L1 and then a context switch occurs to thread 2. At that point, thread 2 grabs L2 and tries to acquire L1. Yeah, that's what I was thinking. That's why I was confused. Thread 1 can hold multiple locks, right? Rather, if this code runs, deadlock does not necessarily occur. Rather, it may occur, for example, if thread 1 grabs L1. So it grabs L1 and then a context switch happens to thread 2. Thread 2 grabs L2. So when it goes back to thread 1, it comes at this line, but thread 2 is holding L2. So it's waiting for thread 2 to complete. And meanwhile, thread 2, when it comes to this line, thread 1 holds L1. So it's waiting for thread 1 to unlock L1. So we are stuck basically. This is a deadlock. As each thread is waiting for the other and neither can run. See figure 32.7 for a graphical depiction. The presence of a cycle in the graph is indicative of a deadlock. The figure should make the problem clear. Then everyone holds this, wanted by this, which holds this, wanted by this. As you may be thinking, simple deadlocks such as the one above seems readily avoidable. For example, if thread 1 and 2 both made sure to grab locks in the same order, the deadlock would never arise. So why do deadlocks happen? One reason is that in large code bases, complex dependencies arise between components. Take the operating system, for example. The virtual memory system might need to access the file system in order to page in a block from disk. The file system might subsequently require a page of memory to read the block into and thus contact the virtual memory system. Thus, the design of locking strategies in large systems must be carefully done to avoid deadlock. In the case of circular dependencies that may occur naturally in the code. Another reason is due to the nature of encapsulation. As software developers, we are taught to hide details of implementation and thus make software easier to build in a modular way. Unfortunately, such modularity does not mesh well with locking. As Julia et al. Point out, some seemingly inertious interfaces almost invite you to a deadlock. For example, take the Java vector class and the method add all. This routine would be called as follows. Vector v1, v2, v1, add all, v2. Internally, because the method needs to be multi-thread safe, locks for both the vectors being added to v1 and the parameter v2 need to be acquired. The routine requires said lock in arbitrary order in order to add contents of v2 to v1. If some other thread calls v2 dot add or v1 at nearly the same time, you have a potential for a deadlock, all in a way that is quite hidden from the calling application. Four conditions need to hold for a deadlock to occur. Mutual exclusion, threads claim exclusive control of resources that they acquire. Hold and wait, threads hold resources allocated to them while waiting for additional resources. No preemption, resources cannot be forcibly removed from threads that are holding them. Circular wait. There exists a circular chain of threads such that each thread holds one or more resources that are being requested by the next thread in the chain. If any of these four conditions are not met, deadlock cannot occur. Thus, we first explore techniques to prevent deadlock. Each of these strategies seek to prevent one of the conditions from arising, and thus is one approach to handling the deadlock problem. Probably the most practical prevention technique is to write your locking code such that you never induce a circular wait. Most straightforward way to do this is to provide a total ordering on lock acquisition. For example, if there are only two locks in the system, you can prevent deadlock by always acquiring L1 before L2. Such strict ordering ensures that no cyclic wait arises, hence no deadlock. Of course, in more complex systems, more than two deadlocks will exist, and thus total lock ordering may be difficult to achieve. Thus, a partial ordering can be useful to structure lock acquisition so as to avoid deadlock. An excellent real example of partial lock ordering can be seen in the memory mapping code in Linux. Comment at the top of the source code reveals 10 different groups of lock acquisition orders, including simple ones such as imutex before immap rwsym, and more complex orders. As you can imagine, both total and partial ordering require careful design of locking strategies must be constructed with great care. Further, ordering is just a convention, and a sloppy programmer can easily ignore the locking protocol and potentially cause a deadlock. Finally, lock ordering requires a deep understanding of code bases and how various routines are called. Just one mistake could result in the D word. D stands for deadlock. Enforce lock ordering by lock address. A function may grab two or more locks. Thus, we know we must be careful or deadlock could arise. Imagine a function that is called as follows. Do something mutex 1, mutex 2. If the code always grabs M1 before M2, it could deadlock because one thread could call do something L1, L2, while the other thread could call L2, L1. For this particular issue, the clever programming can use address of each lock as a way of ordering lock acquisition by acquiring locks in either high to low or low to high address order. Do something can guarantee that it always acquires locks in the same order, regardless of which order they are passed in. Code will look like something like this. Okay. The hold and wait requirement for deadlock can be avoided by acquiring all locks at once, atomically. In practice, this could be achieved as follows. So prevention, L1, L2, unlock. Okay, so one thread holds all the lock. By first grabbing the lock prevention, the code guarantees that no untimely thread switch can occur in the midst of lock acquisition, and thus deadlock can once again be avoided. Of course, it requires that any time any thread grabs a lock, it first acquires the global prevention lock for it. For example, if another thread was trying to grab L1 and L2 in a different order, it would be okay because it would be holding the prevention lock while doing so. Note that the solution is problematic for a number of reasons. As before, encapsulation works against us. In calling a routine, this approach requires us to know exactly which locks must be held and to acquire them ahead of time. This technique also is likely to decrease concurrency as all locks must be acquired early on instead of when they're truly needed. Because we generally view locks as held until unlock is called, multiple lock acquisition often gets us into trouble because when waiting for one lock, we are holding another. Many thread libraries provide a more flexible set of interfaces to help avoid this situation. Specifically, the routine pthread mutex trylock either grabs the lock if it is available and returns success or returns an error code indicating the lock is held. In the latter case, you can try again later if you want to grab that lock. Such an interface could be used as follows to build a deadlock free or ring robust lock acquisition protocol. You have lock, try lock, and then unlock. Not that another thread could follow the same protocol but grab the locks in the other order. The program would still be deadlock free. One new problem does arise. However, live lock, it is possible that two threads could be repeatedly attempting this sequence and repeatedly failing to acquire locks. In this case, both systems are running through this code sequence over and over again. But progress is not being made, hence the name live lock. There are solutions to the live lock problem too. For example, one could add a random delay before looping back and trying the entire thing over again, thus decreasing the odds of repeated interference among the competing threads. One point about the solution, it skirts around the hard parts of using a trilock approach. The first problem that would likely exist again arises due to encapsulation. If one of these locks is buried in some routine that is getting called, the jump back to the beginning becomes more complex to implement. The code had acquired some resources other than L1. Along the way, it must make sure to carefully release them as well. For example, if after acquiring L1 the code had allocated some memory, it would have to release that memory upon failure to acquire L2 before jumping back to the top to try the entire sequence again. However, in limited circumstances, this type of approach could work well. You might also notice that this approach doesn't really add preemption in a graceful way. However, it is a practical approach, and thus we include it here despite its imperfection in this regard. Lastly, mutual exclusion. Final prevention technique would be to avoid the need of mutual exclusion at all. In general, we know this is difficult because the code we wish to run does indeed have critical sections. So what can we do? Leahy had the idea that one could design various data structures without locks at all. The idea behind these lock-free approaches here is simple. Using powerful hardware instructions, you can build data structures in a manner that does not require explicit looking. As a simple example, let us assume we have compare and swap instruction, which, as you may recall, is an atomic instruction provided by the hardware that does the following: compare and swap, address, expected new. Imagine we now wanted to atomically increment a value by a certain amount using compare and swap. We could do so with the following simple function. Instead of atomic increment value while compare swap. Well, instead of acquiring the lock, doing the update, and then releasing it, we have instead built in approach that repeatedly tries to update the value to the new amount and uses compare and swap to do so. In this manner, no lock is required and no deadlock can arise. Though a livestock is still a possibility, and thus a robust solution will be more complex than the simple code snippet above. Let us consider a slightly more complex example, live insertion. Here is a code that inserts at the head of a list. Okay. This code performs a simple insertion, but if called by multiple threads at the same time, has a race condition. Can you figure out why? Oh, the value and the next is changing, right? So that can cause an issue. We are doing head is equal to n, but another thread might like change this. Of course, we could solve this by surrounding this code with a lock, acquire, and release. So lock, list lock, and then unlock list lock. In this solution, we are using locks in the traditional manner. Instead, let us try to perform this insertion in a lock-free manner, simply using the compare and swap instruction. Here is one possible approach. N value to while. The astute reader might be asking why we grabbed the lock so late instead of right when entering insert. Can you, astute reader, figure out why that is likely correct? What assumptions does the code make, for example, about the call malloc? So here is one possible approach. Do next compare swap. And this compare swap function is atomic, right? If I remember correctly, malloc is atomic, right? Hold on, I can't. Let me try to remember. Malloc. Nope. I forgot which chapter it was. Think it's in. Let's try this. Malloc. No malloc. There is a malloc. It has to be somewhere here. I remember we were talking about malloc, and I think it said that maybe the context switch doesn't. No, no. Maybe malloc has his own thread. No, that's not right. I can't remember clearly. I'll have to reread it. Does it even detect properly? It does. Let's see if I can find it. Or I will just search it up after stream. Anyways, code here updates the next pointer to point to the current head, then tries to swap the newly created node into position as the new head of the list. However, this will fail if some other thread successfully swapped in a new head in the meanwhile, causing this thread to retry again with the new head. Of course, building a useful list requires more than just list insert. And not surprisingly, building a list that you can insert into, delete from, and perhaps lookups on in a lock-free manner is non-trivial. Instead of deadlock prevention, in some scenarios, deadlock avoidance is preferable. Avoidance requires some global knowledge of which locks various threads might grab during their execution and subsequently schedule said threads in a way as to guarantee no deadlock can occur. For example, assume we have two processors and four threads which must be scheduled upon them. Assume further we know that thread 1 grabs lock L1 and L2. Thread 2 grabs L1 and L2 as well. Thread T grabs just L2 and thread 4 grabs no locks at all. You can show these lock acquisition demands of the threads in the tabular form. A smart scheduler could thus compute that as long as T1 and T2 are not run at the same time, no deadlocks could ever arise. Here is one such schedule. CPU1, T3, T1. But a deadlock could arise with, yeah, it couldn't actually. Because they need to be holding each other's locks. And then T2 should be done separately. Now that it is okay for T3 and T1 or T3 and T2 to overlap. Even though T3 grabs L2, it can never cause a deadlock by running concurrently with the threads because it only grabs one lock. Let's look at one more example. In this one, there is one more contention for the same resources as indicated by the following. So T3 now uses both locks. In particular, all three need to grab both locks at some point during their execution. Here's a possible schedule that guarantees no deadlock could ever occur. Can we in C assign a CPU to a particular thread? Term best famous as the subject of classic computer industry book Soul of the New Machine says famously, not everything worth doing is worth doing well, which is a terrific engineering maxim. If a bad thing happens, really certainly one should not spend a great deal of effort to prevent it, particularly if the cost of the bad thing occurring is small. If on the other hand you're building a space shuttle, the cost of something going wrong is the space shuttle blowing up. Well, perhaps you should ignore this piece of advice. Some readers object. This sounds like you are suggesting mediocrity as a solution. Perhaps they are right, that we should be careful with advice such as this. However, our experience tells us that in the world of engineering, with repressing deadlines and other real world concerns, one will always have to decide which aspect of a system to build well and which to put aside for another day. As you can see, static scheduling leads to a conservative approach where T1, T2, T3 are all run on the same process. And thus the total time to complete the jobs is lengthened considerably. Though it may have been possible to run these tasks concurrently, the fear of deadlock prevents us from doing so and the costs performance. One famous example of an approach like this is Dijkstra's Banker's algorithm, and many similar approaches have been described in the literature. Unfortunately, they are only useful in very limited environments. For example, in an embedded system where one has full knowledge of the entire set of tasks that must be run and the locks that they need. Further, such approaches can limit concurrency as we saw in the second example above. Thus, avoidance of deadlocks via scheduling is not a widely used general purpose solution. One final general strategy is to allow deadlocks to occasionally occur and then take some action once a deadlock has been detected. For example, If the OS froze once a year, you would just reboot it and get happily on with your work. If deadlocks are rare, such a non solution is indeed quite pragmatic. Many database systems employ deadlock detection recovery techniques. A deadlock detector runs periodically, building a resource graph and checking it for cycles. In the event of a cycle, the system needs to be restarted. If more integrate repair of data structures is first required, a human being may be involved to ease the process. More detail on database concurrency, deadlock, and related issues can be found elsewhere. In this chapter, we study the types of bugs that occur in a concurrent programs. The first type, non-deadlock bugs, are surprisingly common. They often are easier to fix. They induce atomicity violation in which a sequence of instructions that should be executed together was not, and order violations in which the needed order between two threads was not enforced. We also have briefly discussed deadlock, why it occurs, and what can be done about it. Problem is as old as concurrency itself. Many hundreds of papers have been written about the topic. Best solution in practice is to be careful and develop a log acquisition order, and thus prevent deadlock from occurring in the first place. Weight-free approaches also have a promise, as some weight-free data structures are now finding their way into commonly used libraries and critical systems, including Linux. However, the lack of generality and the complexity to develop a new weight-free data structure will likely limit the overall utility of this approach. Perhaps the best solution is to develop new concurrent programming models in systems such as MapReduce. Programmers can describe certain types of parallel computations without any logs whatsoever. Logs are problematic by their very nature. Perhaps we should seek to avoid them unless we truly must. Okay, I will. Actually, I will end the stream here. I was thinking whether I want to do the next chapter. Um, I guess I will leave that for tomorrow, I think. So I will end the stream here, and yeah, tomorrow I'll continue studying the rest of the chapters. Anyways, see you guys next time. Bye.